Okay, so this would be the next part, part 4 of chapter 2. We'll discuss the section on varying benefit insurance. Okay, so this time we take the cases wherein the benefit is not fixed as what we have encountered previously, but instead it is varying. Okay, so consider an insurance with a varying benefit and payable at the moment of death. So again, we first consider insurances which are payable at the moment of death. One type is this: an annually increasing whole life insurance providing a payment of 1 at the moment of death during the first year, a payment of 2 if death occurs during the second year, a payment of 3 payable at the moment of death if death occurs during the third year, and so on. So when t is greater than or equal to 0, we can see that the benefit function b sub t is the greatest integer value of t plus 1. And of course, the discount factor would be v to the t because the benefit payment will be paid at the end, at the moment of death, which is given by t. So the present value random variable z, which is b sub t times v sub t, takes this form. So it's the greatest integer value of t plus 1 times v to the t for any t that is greater than or equal to 0. So the expectation of z will take this integral form, right? So it's the integral of the absolute value of t plus 1, v to the t, ppx mu sub x of t dt from 0 to infinity. And we will use this representation for that net single premium. The capital I will refer to that it's an increasing annuity, no, sorry, an increasing benefit insurance, starting with 1 and then 2, then 3, and so on. And then the bar on top of capital A again would mean that it is payable at the moment of death. The subscript X tells us that it is a whole life insurance. Another type is the one that increases every nth of a year. So an nthly increasing whole life insurance. And the benefit is as follows. It pays 1 over m at the moment of death during the first nth of the year, 2 over m at the moment of death during the second nth of the year, and so on, increasing by 1 over m at the nthly intervals throughout the term of the insurance. So when t is greater than 0, greater than or equal to 0, then the benefit payment, b sub t, takes this form. So it's the absolute value of t times m plus 1 all over m, and the discount factor v sub t is equal to v to the t. Okay? And so this takes the form now of our random variable z. It's v to the t times the the greatest integer value of tm plus 1 all over m. This is greatest integer value, okay? Greatest integer value all over m. And then the net single premium is this form now. So it's the integral of v to the t times the greatest integer value of tm plus 1 all over m times tpx mu sub x of t dt from 0 to infinity. And the upper m here will tell us that it's an nthly increasing annuity. Okay? And then we take note of a special case, that is when m in this net single premium, if we take m approach infinity. So this now we have what we call a continuously increasing whole life insurance. And that will have this as its representation for its net single premium. So there is a bar also on I to denote that it is a continuously increasing. And it actually means the following: the size of the benefit is the size of the benefit if death occurs at time t is t, and so the discount factor will be v to the t. And so the value of z is equal to t times v to the t whenever t is greater than or equal to 0, and therefore its expectation is this, right? So it's the integral of t times v to the t tpx mu sub x of t dt from 0 to infinity. Okay? And then we have the decreasing N-year term insurance. Let's first again consider the one that is payable at the moment of death. So this insurance provides a payment of N at the moment of death if death occurs during the first year, N minus 2 at the moment of death during the second year, and so on until the coverage is terminated at the end of the nth year. Okay, so this is an N-year term. So the policy is enforced only for the first N years. And so the benefit function B sub t takes this form. It's N minus the absolute value, the greatest integer value of t if t is less than n, its greatest integer value. Okay, so it's not absolute value, it's greatest integer value, also with the previous slides. Okay, it's the greatest integer value of t whenever t is less than n. N would be 0 if t is greater than or equal to n. And so we have the discount factor. V sub t is v to the t. And so the value of z takes this form. It takes v to the t times the quantity n minus the greatest integer value of t if t is less than n. N would be 0 otherwise. Okay? If t is greater than or equal to n. And so the expectation is this, right? And then, of course, we want this representation now for the net single premium. So it's an N-year term, so that's why you have this subscript and a 1 on top of x. And then you have a capital D now to denote that it's decreasing, and the bar on top of A to denote that it is going to be payable at the moment of death. Okay? And then let's now consider the case when we have the benefit paid at the end of the year of death. So let's go back to the annually increasing insurance. So this time, it pays a payment of 1 if death occurs during the first year, of 2 if death occurs during the second year, of 3 if death occurs during the third year. And all of these are paid at the end of the year of death, right? So when death occurs during the first year, k is equal to 0, right? If death occurs during the second year, k is equal to 1. If death occurs during the third year, k is equal to 2, and so on. So the size of the benefit, which is b sub k plus 1, is equal to k plus 1. And of course, the discount factor would be v raised to k plus 1. And so the present value random variable z for any k, 0, 1, 2, 3, and so on, is k plus 1 times v to the k plus 1. And so the expectation is going to be this summation, right? The summation of k plus 1 times v to the k plus 1 times kpx qx plus k, where k goes from 0 to infinity. And this would be our representation for the net single premium. So take note that there is no bar on top of capital A to denote that it is payable at the end of the year of death. Okay? And of course, there is a counterpart for this for the N-year term that is increasing. So same thing, the payment is 1 if that occurs during the first year, 2 if that occurs during the second year, and so on until a payment of N if that occurs during the nth year. And all of these payments again are paid at the end of the year, at the end of the year of death. So the benefit function b sub k plus 1 is k plus 1 only when k is 0, 1, 2 up to n minus 1, and 0 when k is n plus 1, n plus 2, and so on. And the discount function is going to be v to the k plus 1, where k is 0, 1, and so on. Anyway, when you take z, this will just be 0 because 0 times v to the k plus 1 is 0. Okay? So the z that we want is this form. So it's k plus 1 times v to the k plus 1 if k is 0, 1, 2, up to n minus 1, and 0 if k is n plus 1, n plus 2, and so on. Okay? And so the net single premium is as follows. So it's the summation of k plus 1 times b to the k plus 1 times kpx qx plus k, where k goes from 0 to n minus 1. And the net single premium is represented by this notation. Okay? And then we have the decreasing n-year term. Okay, the decreasing n-year term insurance that is payable at the end of the year of death. So it'll provide a payment of n at the end of the first year if death occurs during the first year. A payment of n minus 1 payable at the end of the second year if death occurs during the second year, and so on until a payment of 1 at the end of the nth year if death occurs during the nth year. So then, and then the policy terminates at the end of the nth year. So the the benefit function b sub k plus 1 takes this form. So it's n minus k if k is 0, 1, 2, and so on until n minus 1. N would be 0 if k is n, and plus 1, and plus 2, and so on. And again, let's take the discount factor to be b to the k plus 1 for any k. But then what we actually want is z. So this takes the form of n minus k times v to the k plus 1 if k is 0, 1, 2, and so on until n minus 1. N would be 0 if k is n, and plus 1, n plus 2, and so on. This is n plus 2. Okay? And so this would be the representation for the net single premium, right? The capital D again will tell that it's a decreasing annuity benefit and an n-year term. And then this would be the summation form. Okay? Okay. Now, okay. Now, I think I can proceed with the next section, which is actually the relationship between the insurances that is payable at the end of the year of death with that of the insurances payable at the moment of death. Let's start off with this representation. What is this? This is the net single premium of an n-year term insurance payable at the moment of death with a benefit of 1 unit issued to a person aged X, right? So we know that in formula, as an integral, it's equal to this. It's the integral of v to the t tpx mu sub x of t dt from 0 to n. What we can do next is we can break up this integral into n integrals with integrals ranging from 0 to 1, and then the second integral from 1 to 2, and then from 2 to 3, and so on until n minus 1 to n. Okay? And then, of course, we can write that down this way, right? So it's this integral takes this form. It's the summation for where k goes from 0 to n minus 1 of the integral of v to the t tpx mu sub x of t dt, where t ranges from k to k plus 1. Okay? And then if we look at this integral and change our variable from the original t to s, what we do is break up t into the integral part k and then the fractional part s. So t is k plus s. So the integral now takes this form after making the change, right? So dt is replaced by ds, and then the v to the t is replaced by v to the k plus s, the t is replaced by k plus s, and then the t is replaced by k plus s. This mu sub x plus k plus s, it can be written out this way. Okay? And then one trick is to rewrite k plus s px as a product of kpx with spx plus k. Okay, so that's what we're going to do. And then factor out kpx because it's independent of the variable of the integral, which is s. Okay? And then, another thing is to break up v to the k plus s as a product of v to the k plus 1 with v to the s minus 1. And again, v to the k plus 1 is independent of s, so we can factor it out. So we end up with this equivalent form of the previous expression. And then we know that S is fractional, so we can use a fractional H assumption for this. And if we assume UDD, and UDD tells us that SPX plus K nu sub x plus K of S is actually QX plus K. So this whole thing can be replaced by QX plus K, which is also independent of S, so we can take that out. So we end up with this expression. Okay, so the next thing that we can do is to evaluate this integral now, and this is what we have. We note that again v to the s minus 1 can be expressed as v to the negative 1 times v to the s, but v to the negative 1 is 1 plus I. Okay, and then from theory of interest, we know that this integral is this, right? The present value of an annuity that is payable continuously with a term of 1, and multiply that with the accumulation factor of 1 plus I, you get the accumulated value of that annuity. Okay, so this integral now, I think this is supposed to be an S. No, this integral now, this is ds, can now be replaced by S sub 1 bar. Okay, but then S sub 1 bar can also be written out this way. S sub 1 bar is also in theory of interest is the integral of 1 plus I to the t dt from 0 to 1. And so when we evaluate this, we get I over delta. Remember that that log of 1 plus I is equal to delta. Okay? Log of 1 plus I is equal to delta. So at 1, this is 1 plus I to the 1 minus 1. So the 1 cancels out, leaving you with I in the denominator. By the way, the numerator rather, the denominator is a constant with respect to t, right? So it's actually just delta. So it's I over delta. So this is I over delta times the summation. And if you look at the summation, this is actually the same as the net single premium of an N-year term insurance payable at the end of the year of death, right? So assuming the UDD assumption, this would be our relationship between the net single premium of an N-year term insurance payable at the moment of death with that of the insurance that is the corresponding insurance which is payable at the end of the year of death. So there's this factor I over delta that we need to consider. We also get the same relationship if we get the corresponding relationship between the net single premium of a life insurance payable at the moment of death with that of the life insurance, the net single premium that is of the life insurance that is payable, a whole life insurance that is payable at the end of the year of death. You again have that same factor I over delta, right, using these results. Okay, knowing that this is the same, this is true, and that this is equal to this from this argument, and so getting the limit now, we get the following. Okay? Actually, we can derive the same conclusion if we make use of another random variable which we will define as S or S of X, which actually is defined this way. So this is the S that we want, right? Wherein T is taken as K plus S, where we know that K is the integer part of T. So S is fractional. Okay? So we will define the random variable S as T minus K, right? Or T is equal to K plus S. Okay, so we can see clearly that S is the random variable representing the fractional part of a year lived in the year of death of the person aged X. Okay? We note the following, that K is discrete, but S is continuous, right? with its probability mass concentrated on the interval from 0 to 1. Okay? And so, if we look at the joint distribution of K and S, we can have the following. So, the probability that K is equal to small k intersection S is less than or equal to small s, that would be the same as the probability that T is greater than K and less than or equal to K plus S. So, from our discussions in the first chapter, we said that this is actually the probability that a person aged X survives for K years, which is this, times the probability that a person aged X plus K will die within the next S periods of time. So so KPX times SQX plus K. Okay? And then we note that X plus K is an integer, and so S is also fractional, and assuming UDD, we know that S times QX plus K is S times QX plus K. So our joint PDF could be written this way or written this way. But this S actually is the CDF of the random variable capital S evaluated at small s. Right? And then if we can take this as such, assuming that S is uniform, right? Assuming that S is uniform on the interval from 0 to 1. And KPX QX plus K is actually the probability mass function of K evaluated at small k. So what we're saying now is that the joint PDF or the joint distribution of K and S could be broken up as a product of the CDF of S and the probability mass function of K. That tells us that K and S are independent random variables. Okay? So under the UDD assumption, K and S will be independent random variables, and taking S as a random variable having a uniform distribution on the interval from 0 to 1. Okay? And then some basic properties in probability, since K and S are independent, then any functions of K and S would also be independent. So since K and S are independent, then K plus 1 and 1 minus S are also independent. And then also, we note that S is uniformly distributed on the interval from 0 to 1. That would imply that 1 minus S is also uniformly distributed from 0 to 1. Okay, now let's go back to we note that T is K plus S, and we can rewrite it this way. K plus 1 plus S minus 1. And we know that V is 1 all over 1 plus I, or 1 plus I to the negative 1. If we go back to our discussion about getting the net single premium of this life insurance, whole life, payable at the moment of death, we know that it is the expectation of Z, where Z is B to the T, for any T that is greater than or equal to 0. And so replacing T by K plus 1 plus S minus 1, and noting that V is equal to 1 plus I to the negative 1, we end up with the following expression. The expectation of V to the K plus 1 times 1 plus I raised to 1 minus S. But since K plus 1 and 1 minus S are independent, then this expectation can be written out this way. Right? But then we know that this is actually the net single premium of a whole life insurance issued to a person aged X, payable at the moment of death. This is actually Z, right? This is actually Z. And then getting this expectation now, knowing that it is uniformly distributed, that 1 minus S is uniformly distributed on the interval from 0 to 1. So getting its expectation now would have this integral. The PDF would be 1, right? It's 1 all over 1 minus 0. So the PDF is 1. And so we end up with I over delta. Again, noting that delta is log of 1 plus I. So uh, the expectation of 1 plus I to the 1 minus S is I over delta. Okay? So we arrive at the same identity. Okay? And then we can use this random variable S also with the following. Let's look at the n-year term increasing insurance. Again, we note that Z is defined this way from our previous slides. But then we know that the greatest integer value of t plus 1 is actually k plus 1. And again, noting that since t is k plus 1, then we can re-express this as k plus 1 times v to the k plus 1 times v to the s minus 1 for all t that is less than n. Okay? So this expression here is now can be expressed this way. And then, let's use W instead of Z to denote the present value random variable of an annually increasing n-year term insurance payable at the end of the year of death. So earlier we made use of Z to represent that. Let's use W now. So W is k plus 1 times V to the k plus 1, where k goes from 0, 1 to up to n minus 1, and 0 when k is n, and plus 1, n plus 2, and so on. So Z is going to be equal to this Z that we have originally will now be equal to W, since this is W, times V to the S minus 1. Or it's the same thing as W times 1 plus I to the 1 minus S. Okay? Since V is 1 plus I to the negative 1. So taking this form of Z, we can see that W is a function of K plus 1, and K plus 1 and N minus 1 are independent under UDD. Then W and S, 1 minus S are also independent, right? W and 1 minus S are also independent. So, to get the expectation of Z, that would be the expectation of W times 1 plus I raised to 1 minus S. Since the W and 1 minus S are independent, we can write it down this way. Expectation of W times the expectation of 1 plus I raised to 1 minus S. But then from the previous slide, we said that this is I over delta, and this is now the net single premium of an n-year term insurance that is increasing. Okay? So this is the same thing as our expectation for Z is actually, hindi ko nilagay. Sorry. This is actually the one that has the bar on top of A. Okay? This being our Z. So the expectation of this is the net single premium for an n-year term insurance payable at the moment of death. Actually, it's this left side is equal to this expression with a bar on top of capital A. Okay? So we have also the same a similar analogous equation or identity with regards to the insurance that is payable at the moment of death and that of the corresponding insurance payable at the end of the year of death. There is a factor I over delta. Okay? But of course, we make the assumption that S is uniform, right? That the random variable S is uniform. Okay, and we also made use of the fact that we assume UDD during fractional ages. Okay, and so that ends this chapter. We'll try to go to chapter 3 next time, wherein we will discuss life annuity. Okay, that's all.